Hi, everybody. We're here to talk about Chapter 9 in the McMurry textbook on alkynes. Um, Alkynes are, as you may remember, a functional group in which two carbons are sp hybridized. We have two pi bonds instead of one. And so we'll be comparing this quite often to alkenes from the previous chapter, where we saw reactions with those pi electrons. Good news is that this chapter is much shorter in many ways because it draws back to Chapter 8, to the alkenes material. So if as you're going through Chapter 9 you run into some trouble, go back and look at Chapter 8 and you'll see those analogies. Going forward, we will pull reactions from both chapters together and we'll talk about how to use those in practical organic syntheses. So for now, we first start with structure. Remember that the alkyne functional group is composed of two sp hybridized carbons connected by a triple bond. That bond is short, strong, and straight, the three S's here. So we have this very compact structure, and it would involve sort of a linear extension to a molecule. What's shown here is acetylene, so just the two carbon, two hydrogen molecule. But you could imagine if one of these hydrogens were itself a carbon, this would be sort of a protrusion from that molecule. These two pi bonds are available for reaction in much the same way that we saw with alkenes, so we'll draw some parallels there. We'll also see that this hydrogen on the end can be removed relatively easily to create a really strong carbanion nucleophile. Before we can get into all of the meat of this material, we have to talk about naming alkynes. This follows the same rules as alkene naming, in that the alkyne gets priority over other functional groups that might be present. So we give those the lowest possible numbers. Substituents then get the lowest possible numbers after that. We use the suffix of "-ine", Y-N-E, instead of E-N-E, or A-N-E, as we've seen before. And so a 6-carbon alkyne would be called a hex-ine. And then if we have multiple ones, just like we did with alkenes, we'll indicate that by saying we have 2 or 3 or 4, and words like diine or triine. It's a little bit simpler here because the alkyne functional group is straight. We don't have to think about cis and trans functionality. So there is no stereoisomerism at an alkyne center. So here's an example at the bottom showing us sort of the older naming style. We have an 8-carbon alkyne. We've numbered from the right so that we can give the alkyne the lowest possible number. And then the methyl group ends up at carbon 6. So 6-methyl 3-octyne. Or just like with alkenes, we can move that 3 number just before the functional group suffix. And so 6-methyl-oct-3-ine. If a molecule contains both an alkene and an alkyne, we will call it an enine as sort of a category. But we will write it with the alkene first. And this you can think about as alphabetical order. Any of the multiple bond sites are going to be equal in priority as far as numbering goes. And so in this top instance, where numbering from the left or from the right, we would get a 1 and a 6. In that case, we'll choose to make the alkene, the alphabetically first reagent, functional group, we'll choose to give that the lower number. And so we get a 1-ene, 6-ine kind of a setup. Here's the older naming on top. So it's a 7-carbon molecule, that's our hept. And now you can see sort of how this numbering is confusing with the older style. The newer style, in my opinion, is much easier to understand. I have a 7-carbon molecule with a double bond starting at carbon 1 and a triple bond starting at carbon 6. But either is acceptable. In the bottom case, we have a 9-carbon molecule that gives us our non-base name for non-ene. However, if we number from the left, I get an unsaturation starting on carbon 1. If I number from the right, I get an unsaturation that would have started on carbon 2, right, if we had numbered this from the right. And now since I have a clear way to get a lower number, I'll number from the left. So I get a 1-ine in this case, and then the alkene ends up at position 7. Substituents are numbered as they need to be. And so I sort of sum that up here that you give any multiple bond the lower number. However, if there's a tie, it goes to the alkene as the lower or earlier alphabetical substituent. And so you can see that older naming scheme and the newer naming scheme. The newer one certainly isn't great to say, but it's pretty good for writing a very clear name. Okay, so here's some practice that you could do naming alkynes. We've got 1, 2, 3, 4, 5, 6. So a 6-carbon parent chain, that's our hex. Starting on position 3, we have our alkyne, so it's a hexyne, a 3-hexyne in particular. And then we have methyl groups here at 2 and at 5. So 2, 5, dimethyl, 3-hexyne. Same kind of numbering would occur with these guys. This one is an enine, so you'll have to figure out which end to number from. And this one is a cyclo, right? It's a ring structure with a triple bond. Those, because of the geometry, don't happen in small rings. So if we tried to draw like a 6-membered ring with a triple bond, that would be extraordinarily high energy. It'd be really, really stressed. However, this molecule, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's a really, really big cycloalkane, well, alkyne in this case. And so for all intents and purposes, this is flexible enough to accommodate that kind of a straight molecule. It wouldn't really look like this, right? This is sort of shown in the traditional angles, showing us like a 120-degree angle here. In reality, this end of the molecule would be considerably more straight, and then this end would have to be a little more stressed to compensate. So this would just be called a cycloalkyne. You do the naming and numbering the same way that we saw with alkenes. Either this or this, the top or bottom carbon of that alkyne would be carbon number 1. The other one would have to be carbon number 2. Remember, we number through our functional group when we have an alkene or an alkyne in a ring. And you run a number whichever direction gives you the lower priority or lower number for this isopropyl group over here. So here's the answers. There we go. Now, how do we make an alkyne? Well, very much in the same way that we saw that we can do a elimination reaction from an alkene and to generate, from an alkyl halide to generate an alkene. We saw that in chapter 8. If we treated an alkyl halide with a base, we could get an elimination. The same is true here. However, we'd have to start with a vicinal dihalide. Vicinal just means that the two things are on neighboring carbons. Vicinal is from the same root as the word vicinity. So these two are close to each other, neighboring carbons. So we could take an alkene, for instance, treat it with bromine. We saw this reaction in chapter 8. We would get a vicinal dibromide, or what's sometimes called a 1,2 dibromo kind of a reaction. Even if these aren't carbons 1 and 2, which they are in this case, but even if they weren't, we might call it a 1,2 dibromide. So this vicinal dibromide now, when we treat it with a base, I'll say it that way, just like we saw in chapter 8, we saw that if we had one bromine, we could make a double bond. Now, if we have a vicinal dihalide, we can make a triple bond. The base is doing the same thing. So the base would remove the hydrogen here, make a double bond using those bonding electrons, and discharge a bromine as a leaving group. And a second equivalent of base would remove the other hydrogen. Those electrons come in to make another pi bond, and then we discharge this bromine as a leaving group. Once we've made them, that's really the only mechanism we're going to talk about for making these molecules, but once we've made them, now we can talk about using them for reactions. Now in chapter 8, we saw that an alkene, when reacted with HX, reacts by Markovnikov's rule, and we would get that halogen adding at the more substituted carbon. The same is true here. If we start with a triple bond and we react it with one equivalent of HX, which is practically difficult to do, but if we tried to react it with one equivalent, we would get one addition like this. So that's just like in chapter 8. And then a second equivalent would give us now a second addition reaction. Again, just like in chapter 8. So the overall reaction is the alkyne plus two equivalents of HBr to give us this, what would be called now a geminal dibromide. Geminal is when the two bromines are attached, or the two items are attached to the same carbon. So bisanol are neighboring carbons. Geminal, in this case, would be the same carbon. This follows Markovnikov's rule. So down below here, we have an internal alkyne. There is no clear Markovnikov's rule at this point. So when we do our first reaction, we could imagine that halogen bonding to either of these two carbons. However, once we've done that, now we do have a Markovnikov selectivity here. And so we would get a second reaction equivalent, again, to give us a geminal dihalide. The correct answer here could have been the two chlorines on carbon 3 or what's currently carbon 4, although of course we would number it the other way around in that case. My point is, for an internal alkyne, there isn't Markovnikov selectivity in the first step, but there is in the second step. And so the two halogens do end up on the same carbon. If it was an asymmetric internal alkyne, you would get a mixture of products where the two chlorines are attached to one or the other carbon of the former alkyne. X2 addition, likewise, proceeds by the same kind of process as in the alkene scenario. So we still go through a anti-addition. So here's our alkyne reacting with Br2 and some organic solvent. We get the anti-addition. And so by naming standards, we would say now this alkene is the E form of our 1,2 dihalide. It's because one bromine added one side of that unsaturation and the other one added to the other side. Second equivalent of bromine does the same thing. So if we were to color code this a little better, we would have this upper left bromine and the lower right bromine would still be pink from the first addition. The lower left and upper right bromines would be, some other color for this second addition. So at this point, you're probably saying, well, gosh, these look very similar to chapter 8, and it's just happening twice. And in fact, that's true. And so you'll see problems like this. What happens if I react with two equivalents of a dihalide, two equivalents of bromine, chlorine, whatever? Of course, I'll get 4 chlorines attached to the alkyne carbons. If I were to limit it to 1, and we could talk about the practicalities of that, it's not necessarily the easiest thing to limit this reaction. But if we did that, we would say the hydrogen adds to the end carbon, and the bromine would add to the second carbon. And that'd be a Markovnikov kind of addition. If we had this with an internal alkyne, we will get a mixture of products. And there are some nuances here about which one would be major and which one would be minor. Since bromine is quite large, it would be probably more likely to add to the carbon 2 rather than carbon 3, just based on how big the remaining substituents are. But you would get both products. You'd get one with an alkene here and bromine on carbon 3, and one with the alkene here and bromine on carbon 2. Now where things change a little bit is when we get into hydration. Now we still have the two basic processes. We have a mercury catalyzed process that's going to give us a Markovnikov reaction product. And we have a boron catalyzed process that's going to give us the non-Markovnikov or anti-Markovnikov product. So this is similar to oxymercuration and demercuration that we saw in chapter 8 and hydroboration oxidation in chapter 8 to give us the non-Markovnikov. I want you to focus on this in 2 steps. So imagine what would happen just like the alkene scenario, okay? So we've got our Markovnikov selectable alkyne here, terminal alkyne. I'm adding water and I see mercury here. Now notice this is mercury 2 sulfate instead of mercury 2 acetate. Reagent is a little bit different, but you're still going to see mercury here. And when you see that, acid catalyzed water with a mercury salt, I want you to think Markovnikov addition of water. So here the OH goes on carbon 2, the H went on to carbon 1. All right? So that's just like chapter 8. However, we still have a double bond. And what can happen at this point when we've generated what's called an enol, that's an alkene and an alcohol, sharing the same carbon here, an enol. When we've generated this, enols can do something called tautomerization. super cool word. Tautomerization is where we can have a rearrangement here. And what happens is that the hydrogen that was part of the alcohol group ends up getting essentially moved down to this, what in this molecule would be the terminal carbon, the more distant carbon of the alkene pair, to give us now an alkane at that position. And the electrons get moved up here into a double bond. The enol tautomer is actually less stable in most cases than the keto tautomer. And so although these two are in equilibrium, and we talk about keto-enol tautomerization, it's the $1 million phrase here, this exchange back and forth, this really favors the ketone product. And so although this first step, the actual addition step, is very much like chapter 8, what you're going to see is that that tautomerization ends up giving you what the book would call a methyl ketone, or ketone on carbon 2. Okay, so we have an addition of water and immediate rearrangement to the more stable ketone form. By the way, tautomerization also happens in other molecules. So if you look at your DNA bases, for instance, you'll see a number of places where you have an enol scenario in the structure, so something like this, or a ketone, depending which way it's drawn. There is tautomerization there. And that's one of the things that can lead to alternative base pairing in DNA. Now, what if we did this the other way around? If we didn't use mercury, if we used the boron reagent this time and we did anti-Markovnikov addition, okay? I'm gonna jump past these. Okay, if we do that, here's borane, BH3. You'll sometimes see this listed as B2H6. Diborane is just another reagent. So anytime you see boron, you're gonna think about non-Markovnikov addition of water, okay? So just like before, we have the boron forming this crazy complex, technically is a 3-to-1 ratio with the organic material, the alkyne in this case. And then we have treatment with H2O2, hydrogen peroxide, in basic water, gives us that addition of OH. So this bit on the top line is really the mechanism. Okay, we saw that in chapter 8 as well, seeing it again here in chapter 9. However, now we have the possibility, again, for keto-enol tautomerization. Notice, please, that the internal alkyne, again, has no Markovnikov selectivity. So seeing it on an internal alkyne, we could have drawn the OH on either of these two carbons, which means that the ketone could have been on either of those two carbons. In this case, the molecule is symmetrical, it doesn't matter, but if it was asymmetrical, you would in fact get two products. If it's a terminal alkyne, now we do have Markovnikov selectivity, and so we get the same kind of a setup here. We get the same kind of a reaction here, but now, notice we would have added our water, our OH group to the end carbon, carbon 1, and so when we rearrange that, we don't get a ketone because it's on the end carbon, we get an aldehyde. So this is often still called keto-enol tautomerization, even though it's not a ketone, it's an aldehyde. But here we do get that Markovnikov selectivity. Anti-Markovnikov selectivity in this case. And so we have these two mechanisms. I want you to look back at chapter 8, look at how those reactions worked there. Notice that the addition of water is actually the same. We have our Markovnikov addition of that oxygen or a non-Markovnikov addition of the oxygen. The tweak here, the change in alkynes, is that we then have that rearrangement, that tautomerization, to give us either an aldehyde or a ketone. Continuing on through our reactions for alkynes, we have reductions. In the previous chapter, we talked about how you can reduce an alkene to an alkane by adding a pair of hydrogens, usually from hydrogen gas, that's been adsorbed to a metal catalyst, typically platinum or palladium and carbon. We can do that here too. We just do it twice. So we get total reduction. We go from the triple bond in one step, I guess you could say, down to the double bond, but then in an immediate second step, all the way down to the alkene. The reaction is the same in that hydrogen comes from a metal, and so it's a syn addition. And we would just get two reactions, okay, one after the other. We have two other mechanisms. So there is a named reaction here called the Lindlar's catalyst. Lindlar's catalyst is essentially a poisoned version of this catalyst. It doesn't work as well. So it still does the syn addition of hydrogen, but it only does one addition. It can't do the second one. And so we end up stopping at the cis-alkene product. We've only reduced halfway. We'll see in a moment how that works, as well as this other one where we use a soluble metal. So typically a lithium, sometimes a sodium, one of these group 1 metals. There's a few variants of this, but we'll see a soluble metal in ammonia. And that gives us the same kind of one-step reduction, partial reduction, but to a trans-alkene. And so going back to that toolbox analogy, we have three ways to reduce an alkyne. We can reduce it completely using hydrogen and a metal catalyst to an alkane. We can reduce it partially to a cis-alkene if we use hydrogen and Lindlar's catalyst, or we can reduce it partially to a trans-alkene if we use a soluble metal in liquid ammonia. And so here's Lindlar. Again, the two hydrogens are being added from that metal surface, and so they're added in a syn addition, add to the same side here, and that gives us a cis product. Remember the language here. So syn addition means the two pieces come from the same direction. The product is called cis, or Z if you want to use that language, because of the resulting structure of the product. This would be further reduced by plain old hydrogen and platinum or palladium all the way to the alkane. However, Lindlar's catalyst would stop right here with the cis-alkene product. If we wanted the reverse stereochemistry, if we wanted a trans product, we would use a soluble metal, typically a group 1 metal like lithium or sodium metal in ammonia. And again, now it's an anti-addition, which ends up giving us a trans-alkene product. The mechanism here is really tough, and we're not going to talk about it beyond me saying that it's tough, but if you want to take a 400 level organic class somewhere, you might get into that. Mechanism's tricky on this one. Just remember it as a tool. So we have three tools to reduce alkynes. We can reduce them completely with hydrogen and a metal catalyst, partially to a cis-alkene with hydrogen and the Lindlar catalyst, and partially to a trans-alkene with a soluble metal in ammonia. We also, like alkenes, we can cleave alkynes with very strongly oxidizing agents. Typically, we talk about potassium permanganate, or we talk about ozone. We could talk about some chromium salts here, chromate or dichromate. But the maybe thing to pay attention to here is that if we have part of the alkyne, okay, one of the carbons of the alkyne that's connected to a carbon, we get terminal oxidation. We go all the way up to the 3 bonds to oxygen setup. That's as high as that could go without breaking this carbon-carbon bond. And so we end up at the carboxylic acid state. So imagine we're cutting this internal alkyne right in half and making both of those 2 carbons carboxylic acids. And it doesn't matter which oxidizing agent I use. That makes it a little simpler than chapter 8 when we had to be a little more finessed about which one we were using. If we have a terminal alkyne, the internal side of it is exactly the same as this, so we get a carboxylic acid. However, the side that's at the end, that's connected to hydrogen, we can break that CH bond. We couldn't break the CC bond over here with this mechanism, but we can break the CH bond. And so if we have a terminal alkyne, that last carbon, the terminal carbon, gets oxidized all the way up to the 4 bonds to oxygen scenario, or carbon dioxide. This is a really important reaction because what we've done is we've shortened our carbon chain. All right, if we started with a 6-carbon terminal alkyne, we now have a 5-carbon carboxylic acid, and we've cut off 1 carbon as CO2. The last reaction that we're going to talk about is taking advantage of the acidity of that CH alkyne proton. Now, this end proton here, as we can see in the chart, a typical alkane CH bond, that hydrogen has a pK of around 60. It's basically not removable. We saw that we could remove it using a radical reaction if we wanted to replace it, do a substitution with a halogen. And that's how we functionalize an alkane, to put that halogen on, and then we can do some stuff. Now that we have the halogen, we can do elimination reactions to get an alkene, for instance, and then we can do other things. So starting with an alkane, we really don't have a lot of options. We can do some radical chemistry. Once we have an alkene, we have this pi bond. We can do all kinds of addition reactions, and that's great. We saw all of those before. However, those hydrogens still don't get removed. They're still too firmly attached. They're not acidic enough to be removed with any practical basis. However, by the time we get to an alkyne, the pKa is less than half of what it was for the alkane. Remember that pKa is a log scale, so every number we're going down is actually a tenfold increase in acidity. So we are quite a bit more acidic here. Still not acidic enough for hydroxide to remove this, but we do have a base called the amide ion, the sodium amide in this case. It is strong enough. And so if we treat our terminal alkyne with sodium amide right here, we can remove that end proton to generate what's called an alkyne anion. Okay, they sometimes use acetylide here. Acetylene is the common name for a 2-carbon alkyne. So depending on what this R group is, if it was longer, it wouldn't be acetylide anymore, but it would be an alkyne anion. This thing is what I alluded to in the beginning of today's discussion, that this now is a long, straight, strongly bonded nucleophile here. I have a carbanion where that negative charge is way out on the end of this sort of promontory from the molecule. Think of this as, in nucleophilic terms, as a spear. This is a really potent nucleophile, and we can use it as such. So one of the most common ways to do this is to generate the alkyne anion here, and then use it to do a substitution reaction on an alkyl halide. And when we do this, now we've extended our carbon skeleton. I don't like that this is backwards, but I left it this way because it's how it is in the book. Notice that the 2 carbons over here with the triple bond are still there, right? The triple bond didn't actually participate in this reaction. So you can sort of backtrack this by finding the alkyne in your product right here. But we've extended the carbon chain with the CH3 group right here. So we started with, in this picture, a 2-carbon alkyne, and we've added 1 carbon to it. So just like we saw the permanganate or ozone cleavage of a terminal alkyne can give us 1 carbon shorter a molecule, and really all of those cleavages can make the molecule shorter, but that gives us the 1 carbon shorter. This kind of reaction can give us an extension. There are some limits to it. It works best if this carbon here, this alkyl halide, is either a methyl alkyl halide, like we're showing here, or if we had a primary alkyl halide, like is shown here. Okay, that would work. And so we're seeing another couple examples here. We've got acetylene treated with sodium amide. Of course, remember, we do have hydrogens on both sides, so we'd have to be real careful here. We could get removal of either of these, or maybe both of these, okay? They're showing us removing the one on the right. That nucleophile now can attack the alkyl halide carbon to extend the carbon chain. And notice we have an R group here now. This is a primary alkyl halide. Whatever that R group is would still be attached over here. Here's a terminal alkyne, same kind of deal. I remove that hydrogen. I do what I'm going to do here. I attach there, and now I get an extension of that carbon chain. And I still have the pi bonds that I can do other chemistry with. So I could hydrate those to make an aldehyde or a ketone. I could reduce them. I could add halogens. I could do all sorts of things. So I've made the molecule bigger. This is a really common reaction in synthetic chemistry, that you can build up a large chunk of the molecule with an alkyne group on it, and a different large chunk of a molecule with a halogen on it, and then you can react those two together in a substitution reaction. And so here's basically what we've covered. Okay, we can go from an alkyne to an alkene by partial reduction. We have the two mechanisms to do that depending on the desired stereochemistry outcome. We can go full reduction. We can generate an aldehyde or a ketone here and here based on hydration. Two different mechanisms, right? Two different tools. We can add halogens. Okay, they're showing us that we've added one halogen here. We'd have to think about how we did that. That's maybe a two-step reaction. But we could add one halogen. We can add two halogens. We could add four halogens. We can get over here to adding an alcohol group at the end. Right? How would we have to do that? Well, not direct hydration, because that would get us one of these guys. But maybe we could do a reduction first, and then a hydration. We can extend the carbon chain by the mechanism we just talked about. And if we pull in some Chapter 8 chemistry, we could do an epoxide formation. We could do a partial reduction, and then treat that with a peroxy acid. So the point here is that we have lots and lots and lots of options. We have lots of tools in our chemical toolbox, and we can do all kinds of good chemistry using a combination of the Chapter 8 and Chapter 9 reactions. And that's what organic synthesis is about. Okay, so depending on when you're watching this, I guess the statement at the bottom about the next lecture might not be totally accurate, but what we're talking about here is using all of these tools to figure out how to build a molecule. So it's often helpful to work backwards from the product just as much as it is to work forward from the reactant, okay? You can focus on the functional groups. So look at what you have and what you're trying to get, how many carbons you're dealing with, and use those tools that you have available to yourself. And don't get frustrated, all right? There's lots of ways. Sometimes there's multiple routes to get to the same problem, and one might be better than the other, but as long as you have one that works, that's what we're looking for. So these reactions that we know, we can make alkenes and react to them. These are Chapter 8 things. And so we talked about how we can make an alkene by base treatment of an alkyl halide or acid treatment of an alcohol. We can react those alkenes in several different ways using halogens. So adding HX or X2 or X2 and water. We have two different ways to make alcohols depending on the selectivity you want, Markovnikov-regioselectivity. We can reduce them to alkanes. We can make them into diols in a couple different ways, again, depending on the stereochemistry you're looking for. We can make them into carbonyls by cleavage. We can make them into cyclopropanes, and we can make them into epoxides. All of that comes from Chapter 8. Here in Chapter 9, we talked about how we can make alkynes in a very similar method, but from a 1,2-dihalide, a vicinal dihalide. And then we can react those alkynes, again, to halides, different ways. Carbonyls by hydration and tautomerization. Alkenes by partial reduction, alkanes by complete reduction, and alkylation, or chain elongation, using that alkyne anion kind of a setup. Now, at this point in the course, I strongly suggest that you go through these two chapters, Chapter 8, Chapter 9, alkenes and alkynes, and write out all of those reactions that you've studied. Now, the textbook gives a summary of reactions, and that's great, but don't just print that out, and don't just use that. Write it out with an example. I like to call this a reaction book. So go through, look at each reaction, write out its name, write out a simple statement of what it does. I would include a page number or a section number from the book so you can go back and follow up on details if you need to. And give yourself an example of how that thing works. So any special considerations or any particular reagents or anything like that that you need. Putting all of that together in one place helps you to organize your thoughts, and it really helps with the synthesis product problems at the end here. This is an example. So here we're saying come up with a mechanism to synthesize cis-2-hexene from 1-pentyne. Okay, so we draw it out. Here's cis-2-hexene and here's 1-pentyne. Well, what's changed? Start with the logic here. Well, pentyne is a 5-carbon and hexene here is a 6-carbon. So I need to extend the carbon chain. All right, I know how to do that with an alkyl halide, so that's good. I also need to go from a triple bond to a cis double bond. I know how to do that with partial reduction. So I have two steps. Where do we start? Well, you can either write out how you would extend the chain to go from a 5-carbon to a 6-carbon alkyne. That's sort of a forward direction. Or you could think backwards and say, well, I need to make a cis alkene. I know how I could have done that from an alkyne that had the right number of carbons, and I would do it this way, one of these two things. Okay, so you can go forward or you can go backward, it doesn't matter. But once you do it, either way, you'll come up with this idea. Step 1, I need to have treated with sodium amide to remove that proton and create my pentyne anion. Then I'm going to react it with a methyl halogen. It doesn't have to be CH3I, it could be CH3Br or whatever. But that will extend my carbon chain by 1 to give me a 2-hexyne. Now I've added on this end carbon. And then I need to partially reduce it. I'm going to use Lindlar's catalyst because I want that cis product at the end. Another example, synthesize this molecule from acetylene, a 2-carbon alkyne, and an alkyl halide. Well, how do we want to do this? Okay, there's a few options. I do need to go from a 2-carbon to a 5-carbon, which tells me I'm probably going to need a 3-carbon alkyl halide right here. Okay, I can do that. And then I need to go from that alkyne to a single bromine attached in the Markovnikov fashion. Okay, so how do we want to do it? Well, again, I can think about it. I can think about it like this. Maybe I want to go backwards. Well, how could I make this alkyl halide? The only way I know to do this, to put one bromine on, is if I had an alkene. And that would have to have been a terminal alkene plus HBr. Okay? So I could do either one of these, right? Technically, either one would possibly do it. The bottom one doesn't have Markovnikov selectivity, and so I'd get some product that had the bromine over here on carbon 3 where I don't really want it. I'd get some on carbon 2, but I'd get some on carbon 3. The better approach would be to use the top one, because I do get clear Markovnikov selection. I would only get bromine added on carbon 2. All right, so the top one would be my best bet. So that's my first step backwards. If I want this product, this 2-bromopentane, I will need to have immediately preceded that with one pentene, one pentene, and treated it with HBr. Yeah. Now, how did I get one pentene in the first place? Well, now I want to say, all right, I could have reduced the alkyne to get an alkene, or I could have started with an alcohol, or I could have started with a halogen, right? There's 3 ways we know that we can make alkenes at this point. This problem specifically told me that I was going to start with acetylene, right? I had to start with that 2-carbon alkyne, so I have to pick this one. If we didn't have that problem, that limitation, I could have drawn up a mechanism where I started with one of these other guys, okay? Question now is, now that I know I need an alkyne, well, which 2 carbons are my acetylene? And they're going to be the same 2 carbons that are ultimately the alkene. Okay, so carbons 1 and 2 here are my triple bond reagent. That means I need 1, 2, 3 carbons. Oh, this is the reaction that we're talking about. Okay, I could have used either of these to get my alkene. Okay, because the stereochemistry doesn't matter in this case, I could have chosen either one. Now that alkyne, that 5-carbon alkyne, again, which one was acetylene? Well, these 2 carbons at the end would have been my acetylene, which means that these 3 carbons over here must have been in my alkyl halide. And so I get something like this. All right, my acetylide anion reacting with a 3-carbon or an N-propyl halogen. Okay, bromine, chlorine, iodine, whatever. And then I get my product. The new bond has formed here between carbons 1 and 2 and carbons 3, 4, 5. So my overall scheme looks like this. I need to start with my 2-carbon acetylene, treat it with sodium amide to produce the anion, and then react it with a 3-carbon alkyl halide that extends my carbon chain by 3. Then that needs to be partially reduced. I could use either of my partial reductions to get the terminal alkene, and then treatment with HBr gives me my desired product. Synthesis like this is challenging, and it really does take practice. It takes a lot of work to look at all the options and sort of that creative flair to figure out how to pair them together, but you can do it. It just takes practice. So go into the textbook, look at the section on synthesis, look at some of the additional problems, the in-text problems, practice, 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 and use that study guide and solutions manual to help you out. And I like to joke about this. We talk a lot about organic synthesis and total synthesis of biologic materials. This is vitamin B12, and this is one of those examples of doing chemistry because you can. Typically, vitamin B12 is isolated from natural sources, and then it would be purified and put into a pill that you could take, as a vitamin supplement. But this mechanism was worked out to build this gigantic molecule. It just took, a couple of countries, about 100 students and postdocs, and about 10 years of concerted work to figure this out. So this won't be the final exam question. It's supposed to be a joke, but the point is that no matter how big the molecule, it can be built with simple reactions. Of course, depending on the details, there's going to be a lot of purification. There's going to be a lot of testing and nuance, and reaction conditions are very, very important. But for everything that we're going to do, you're going to be using those reactions from Chapter 8 and from Chapter 9. And so, pardon the scrolling real quick, but if I go back, these are the reactions you want to know. Write them out in a reaction book so you have everything handy at your fingertips, and then practice, practice, practice. With that, keep up the good work, folks. Email me if you have any questions, and otherwise, have a great day.